So let us use MATLAB to approximate values of this integral by using Riemann sum. So first, a good idea is to look at a graph of this function. So for graph, let's just first go to MATLAB and ask for a new live script. That has become my favorite now. Okay, so once we get the new live script, what I would do is that I will just give it a enter symbolic variables, and then I would do this. Let's give our function, since it's based on logarithms, name lxy, right? And then I will just say 1 divided by, and MATLAB, as you know, takes log for natural log. So keeping that in mind, we will enter the function. All right, so here we got the function, and then after that all we have to do is just ask it for a surface graph of this function. So we want to graph this L over the interval. Remember this, that we were going from 0 to 10, then 0 to 10. And once I do that, and remember this, that in this case you have to press Control Enter to get the graph, or get a graph rather. So here is a graph. Let me just open it in the main window. Okay, so it's coming up. Where did it go? It's taking, okay, here it is. All right, so if we look at a graph, all right, then here is a graph of the function, and let's have it start at the bottom from 0. So we will go ahead and modify this by saying this, that we want our axis as this, 0 to 10, 0 to 10, and then say 0 to remember the top was automatically about 0.45. So again, I'm pressing Control Enter in the live script. All right, so here is a new graph for us. Okay, come quick please, here it is. All right, so here is a graph that I want to approximate the integral of, or in other words, what we want to do is to find the volume over this square, 0, 10, and then 0, 10, and under this surface of 1 over natural log of 10 plus x square plus y square. Now the graph is pretty nice and smooth. You can make it smoother by doing this. That go back to your script and just change the mesh density here. So sorry. So here comma, and then I will go mesh density, and let's increase the mesh density to 60. I think its default is 35, and you will see the graph would be smoother. Okay, but it's become much smoother, but I want to make the graph really not that smooth. So let me just decrease the mesh density. All right, so I decreased it, and now we will work with it again. So come up, it's right here for us. Okay, so now you can see that our graph looks like this, and for simplicity I'm even going to go ahead and change the color of the graph. Okay, all right, come up please. So here it is, and let's change the face color to plain and simple. Let's just keep it like gray. That's not too bad. Okay, so here it is, right? So we have a graph here, and now the graph is a little more clearly visible. So let's go to the next part now. So what we are doing here is this, that we shall just go ahead and just approximate the value by taking the volumes of rectangles over subdivisions. I could have done the whole thing as a rectangle, that I will do in a minute. All right, so this is one rectangular box, I should say, sorry, and we'll just stretch it around this whole thing. Okay, so what I meant by taking one rectangular box was this, that I can go to the midpoint here, and the midpoint in here for this rectangular region is going to be 5, 5, because you know that we are talking about this rectangle, right? So 5, 5 is the midpoint, and the next part that we do is make a rectangular box with this base and altitude how much? The value of the function at 5, 5. Okay, so we are doing what you call midpoint rules, one of the many rules that you can use, right? So it's about, say, 0.24. So let's go back to our drawing board, all right, and make a rectangular box with an altitude of 0.24. So we will have MATLAB make it for us. So let's go back to our live script and ask it to hold on to the earlier graph. All right, and then I'm going to define another function. Let me just call it mxy. And the way it works best for me for the constant functions, because MATLAB has its own style and I know very little about it. So that's how enter it, and right here we got this. So I'll just put the values 0.5 and 0.5 here, and just press, and then we will just ask it to just add this graph here, the other graph that we have. All right, feel free to fast forward, yeah, if I am boring you too much. Okay, all right, so here we go, and I think that rectangle should come up, and here the rectangle is. So something went wrong. Let me check what went wrong. Okay, so what went wrong? Oh yeah, what went wrong is this, that I have lost my focus now. All right, so, and that happens. So since it is a teaching video, I wanted to keep the mistake, and here is the new graph, and the yellow graph is staying, okay, because I didn't ask it to hold off. So let me just make the whole thing in a new window for you, or just let me just remove this yellow graph, and I'm going to go off the screen for a second. So let's go ahead, and I am just going to bring it into the regular window, and I'm just going to edit it out instead of asking it to, instead of going to new graph and everything. So here it's out, and now all that we will do is this. Okay, and that is tools, rotate. Okay, here we go. All right, so now what I'm going to do is that I'm just going to insert lines to make it, or just a moment. Okay, so here I don't have to really do it this way. You have the idea of what's going on, that I'm just making the box in a very, I would say, in a very unintellectual way, but that's okay. So you know what's going on. So let me just stop it here, and I mean my class. Okay, so if we compute the volume of this box, what I would get is this simply. What I would get is, let me go back to scientific notebook here, that if I calculate the altitude, it was 0.244 and all that, and then say I multiply it by 100, which is the area of the base, okay, because we are going on 0, 10, 0, 10, so that's 24.4239. And before MATLAB, let's just look at an approximation of the value here. So here is the value approximated by Scientific Workplace that I'm using, and here is a value if we just take it as one rectangle, and we are having a departure of like 0.45 approximately, in my 0.456 rather, or 0.455. So let's go ahead and take more and more rectangles, all right, and see how the approximation comes up, or how the approximation changes. So now we are back to our original drawing board. So here what we have done is this, that we have subdivided each interval into 10 subintervals of length how much? 0 to 10, 10th of 10 is 1, so 1 unit each, or I have 100 is 100, square, like tiles of area, 1 square unit each. So if we go further, what we will notice that if we again take the midpoints, okay, let me just do this here. Let me just make a display of the base only. So now this is our base, and we have all the midpoints here of the 100 tiles that we have here. Okay, and if we look at the coordinates of the midpoints, what we will do is, let me just make them bigger a little. So here what I have done is that I have brought this first row up here, and what we can notice here is this, okay, that the coordinate of the midpoints of the squares in this row are 0.5, 0.5 here. Now this will become what? 0.5 or 1.5, and that's how we go along this row. Okay, so if we look at this thing, notice how the first coordinates here are changing. I got 0.5 and 0.5 again here, and then I have 1.5 as my next coordinate, so that's 3 times 0.5, right? And then 0.5, and then for the next one I have, this is 2.5, so this is 5 times 0.5 and then 0.5. All right, and going in this manner, what do you notice here? This is 19 times 0.5 and then 0.5. So in other words, the way this first coordinate is changing in here is this, that it goes in the multiples of, or in the odd multiples of 0.5, where n is ranging from where to where? 0, 1, 2, and all the way up to how much? 9, right? Now, on the other hand, notice this. Say, for instance, I am at this place. So here what I got, excuse me, here I'll have 7.5, right? That's this coordinate. And then when I go up, so if I go in this direction, what I get is that I get 1.5, 2.5, 3.5, 4.5, 5.5, and then 6.5. So what are these? Just as before, the first coordinate is 15 times 0.5, and the second one is 13 times 0.5. So if I look at the variation of the second coordinate, that also goes the same way. That is odd multiples of 0.5, and they don't have to be equal. Keep that in mind, where m varies from 0, 1 through and all the way to how much? 9, right? Okay, so now let's see how we put that in summation form and do it like, just like arithmetically before bringing MATLAB into the picture. So now let's come back to scientific workplace, okay? And here what we have is that we have the double summation, right? And say in the interior we are going to have n varying from 0 to 9, remember in the previous one. And here also we have n varying from where to where? 0 to 9, right? And then what we get for the function is that it is 100 and then 0.5 times 2n plus 1 square, right? And then for the second coordinate we have, what do we have? Instead of n, we will change the index to m. All right, and here we are just formally writing 1 cross 1 just to stress that area of each of our subdivision is 1 unit. So let's see what it gives us. It should give us a little finer approximate. And what I made a mistake here again, didn't I? Right, I have to have squared the whole thing. Okay, so let me do that. Sorry about that. Okay, so here we go. Okay, and then let's approximate it now. So what we have is, we got a little better approximation, right? And we can continue it in the same way. Let's just erase this part here so that things stay in the recording area. So if you want, I mean, we made like 100 subdivisions. Now you can do this. That is, just go ahead and take the squares of side like 0.1, 0.1. So what will happen is this changes to 0.05 for the midpoint, right? And what will this guy change? From 9, I think it's going to change to 99 because we have taken 100 subdivisions on each part. And then, okay, it's taking a few seconds. So it's taking a lot more than few seconds, but that's all right. Okay, it should come up soon. Okay. Here it is. And then you can see that this approximation is like better than the earlier one, as you would expect, because if you recall our earlier picture, so you can see over in this area we have a rectangular box quite well doing things, but as you go on this side you can see a big departure from rectangular boxes if we just stay to 1 by 1 side, all right, or size rather. So let's go ahead and make finer subdivisions, and we will make them for equal lengths, and I'll leave it for you to have fun with different lengths. Okay, so now let's go back to our original MATLAB window, all right, in live script, and I think this much is well visible. And what I want to do now is that I want to do computations using MATLAB of what we did using the scientific notebook before, right? Okay, so what I will have to do first is this, that now I'm not going to do any symbolic calculations, that I would define what MATLAB calls an anonymous function or function handle, that is f at x, y. Okay, I'm just going to ask it to take the value of f at any given xy. So you can see that I typed in the same function, but before a multiplication or division sign or power sign, I have to put a dot beforehand, because otherwise we will not get element-wise multiplication here. All right, so just, and you don't have to put that before plus or minus sign. So we did that, and now we are going to look at our subdivisions. So remember, these subdivisions are h and k, that's what we are calling them. That is, in the very first calculation we took the 10 subdivision of each of the intervals, so we are just calling h as 1 and k as 1. And then after that, what we would do is that we shall define the points P from, so what I would do is this, that we are going to go by midpoint, and I want to do this. I want to be able to just vary the value of h when we go ahead and make it finer. So I'll say that start with 0.5 times h first, which for practical purposes is just 0.5, and then go in the intervals of h, and then where would it stop? Our end point is 10, so I'll say stop at negative 10 minus how much? 0.5 times h after that. All right, and here I will insert a semicolon, because let me just show you what will happen if I don't. Okay, I'll have to press Control Enter to show you what will happen. Okay, first of all, we'll lose time, and then it's just going to display the whole thing here for you. And if we don't want that, let's put a semicolon there. Now for the other one, we are doing the same because our h and k are of the same length and our intervals are also of the same lengths. So we'll take p and q as of the same length. So again, let me just quickly show you what this means, because I have been saying it and I don't know how clearly I have been saying it. So let me first copy it and bring it here. Okay, so just quickly change the font size. All right, so here is what we have. Okay, and then let me explain what we are trying to do here. Okay, so you may have already gotten what we are trying to do here, but anyways, first let's look for this part here, and you can see we are taking, see, our k is 1 unit and so is our h, right? And then what we have is this. Let me bring it to a writable area right here. So when we are talking about p, so what we are asking it to do is do 0.5 times h, so it did 0.5 times 1, and then go in the increments of h, that is, just keep going 1 unit further. I didn't do a good job of sketching it. Let me just change it. That is, by that it means just go by 1 unit steps of 1. All right, and where do we stop? We stop here, 10 minus 0.5 times h, right? And the same thing we will do for what? The columns, right? Okay, that we are starting at 0.5, and then here I should have changed it to k, because h and k sometimes will be different. I'm going to change it once we get there. And k is also what here? 1. But again, h and k, they don't have to be the same. So start here and keep on going until you get what? 0.5 below the upper limit of 10. Okay. So once you do that, what we will do is that we will ask MATLAB to take all these like a grid of points. Okay. And so here we are back on our live script. So let me quickly change this to k, even though here it does not really matter, but anyways. So here we changed it to k, and then what we would do is that we shall form a grid with all these points p and q, and then let z be the values of f here evaluated at these points, and they will serve as what? As the altitudes of our rectangular boxes. And now you can define the Riemann sum as, we are putting the double summation here. It will compute the columns first, but anyways, z gives us the altitudes. Okay, all right, and then these are the areas of the bases of those rectangular boxes, h times k. And if we do control enter, as we should for for this, here we get the value of Riemann sum for h and k equal to 1 each. And if we do format long, it will display values for longer, for more than 4 digits after the decimal sign. Here it is. Okay, and an advantage is this here, that if you want, you can just go ahead and change the step size. All right, and there we go. And when we say, again, when we compute it, here is the new sum. All right, you can even go and make your partitions, or make your number of partitions longer. All right, and then if you do that, you can see we get this value here, 24.8791, and etc., etc. And we did this, that we calculated this integral by using scientific notebook or scientific workplace. So we are just asking for an approximate integral of this f, which we had defined as an anonymous function right here, and we will take it over the range of xy values from 0 to 10 to 0 to 10. Press Control Enter. It should come up. Okay, it's still calculating. Should be here soon, hopefully. Yes, it is, and it's not visible here in the window. So yeah, here it is. And you can see that we have a very good situation up to what? Up to 3 and about 6 digits after the decimal sign, right? For when we took the larger number of partition points, and we are looking at an approximate integral evaluated by MATLAB.